Hi, everybody. Today we're going to circle back to our work with the steel tape. And we're going to talk about what corrections we need to make on a steel tape when we measure distances. So for those of you in engineering surveying, this material corresponds to about chapter 6 in your textbook. And for those of you in practical surveying, this corresponds to chapter 3. Although the material that I present today will be pretty much self-contained on this worksheet that I'm going to give you, that we're going to talk about today in the vlog, and then you'll be asked to do for homework. The worksheet and my notes will be posted to Moodle, and the due dates are posted as well. So with that, let's get started and talk a little bit about what happens with the steel tape. When you use a steel tape to measure distances, there are 4 main corrections that you have to make. The first one is for the slope of a tape. In other words, if you are measuring a distance that is not horizontal, you need to correct the slope distance, which is what you would measure, to a horizontal. And the correction factor, if you think about it, a slope distance is always longer than a horizontal distance. So anytime that you have a slope correction, if the slope distance is longer and you are going for the horizontal correction, you would take the distance along the slope and subtract the correction for the slope in order to get the horizontal distance. Or if you have a horizontal distance and you're given a correction for slope, then you would add it to get the slope distance. But the important thing to remember is the slope distance is always longer than the horizontal distance. Okay, so when you're determining whether you add or subtract the correction. So the first part of this worksheet, as you can see right here, is the correction for slope of a steel tape. In other words, if you're measuring on an area that's not level. And it gives you 3 different forms of the correction. One is for a gentle slope where the slope M is less than 20%. One for a steep slope where M is between 20 and 30%. And one for a very steep slope where M is greater than 30%. Now for our purposes, we are always going to be using the correction for a gentle slope. Or in other words, this equation right here, which is C of H, which is the correction factor, is equal to h squared over 2 times s. And those variables are defined down here. H is the vertical distance, so if you have 3 feet of drop, for example, that would be your h. We're not going to have to use theta, but theta would be the angle if we have this very, very steep correction. And s is the slope distance. So in other words, you would calculate this value of c sub h, then subtract it from the slope distance to get the horizontal distance, or add it to the horizontal distance to get the slope distance. Each one of these correction factors will either be added or subtracted from the horizontal distance, either the corrected distance, the actual distance, or the corrected distance. And if you have more than one correction factor, you can just add them in series. So for example, if you have a slope correction and a pole correction, which we'll talk about in just a moment, then you just add one to the length or subtract one from the length and then add the second one. So they don't compound each other in any way. And they're also very, very small. So if you have a 100-foot pole, you wouldn't expect a correction of more than 1/10 or so of a foot, and that would actually be quite large. All right, so our second correction. The second correction factor that we have to think about is a correction for temperature. If you think about it, a steel tape will expand a little bit, get a little bit longer if the temperature is hot, and will get a little bit smaller if the temperature is cool. Now, in general, steel tapes don't expand or contract very much. However, if we're measuring long distances or if we're pulling the tape multiple number of times, we have to make an account for this correction. So whereas the slope correction is always subtracted from the slope distance, a temperature correction can be either positive or negative. Okay, so temperature correction, let's see, C sub F is what we're calling it, can be either added or subtracted. And the way that we need to think about this is what's going on in terms of the tape being longer or shorter. So if the tape is longer, that means that the temperature is higher than the standardization temperature. And what happens then, think about this for a minute, if on the ground, the actual measurement, you had 100 feet, okay? If the tape is long, that means that the tape is going to register, say, 99.9 feet, for example, because there would be a little bit of an overhang for a longer temperature. So that means that from the ground, which would be 100 feet, you would take the taped distance plus the correction if the tape is long. If the tape is short, that would mean that the temperature is lower than the standardization temperature. And it would be exactly the opposite. On the ground, if we had, say, 100 feet, the tape would come up short, and you would have a little bit of a correction that would have to be, well, in other words, if you have the ground number would be 100, let's do it this way because I want to write it the same way. The ground number would be 100, but the tape number would be actually longer than that. So you would take the tape distance and subtract the correction from that in order to make this correction. Now, the temperature correction is always equal to C, which is the coefficient of thermal expansion. That number is given to you right here. It can be a little different from tape to tape, but in general, 6.45 times 10 to the negative 6 per degree Fahrenheit is a pretty common temperature. T sub S is the temperature at which the tape was standardized. It's almost always 68 degrees Fahrenheit. And T here is the actual temperature, and L is the measurement that we have taken. So in other words, that would be the tape measurement, right? So this temperature is the temperature, like if you're working on the highways, you're measuring a tape, you're measuring a length, and the temperature outside is 80 degrees. This would be 80 degrees. This would be 68 degrees. This would be the number that you read on the tape, right? And this would be 6.45 times 10 to the negative 4th. Now, if this number comes out to be a negative or a positive, you can think about it that way, or you can just think about adding or subtracting depending on whether the tape is lengthened or shortened. Either way, but don't do them both. In other words, negative negative is a positive mathematically. Don't put both of them in because then you'll kind of undo your own work. All right, the third one is a correction for temperature. Excuse me, for tension. We had talked about this when we talked about using the steel tape. Generally speaking, you give the, when you're measuring from one point to the other, you give the tape a good snug pull. All right, snug is about 20 pounds. It means that you're pulling on it with a force of 20 pounds. Now, if you pull with a force less than that, the tape will be a little bit short. And if you pull with a tape with a pull stronger than that, the tape will be a little long. So we have to have a correction for pull. Now this is different than a correction for sag, which we're going to talk about in just a moment. Sag is kind of one of the harder ones to figure out, but it's not that difficult. You'll be fine. But basically the correction for pull just has to do with the elasticity of the tape. So the correction for pull is equal to PM minus PS times L over AE. And let's define all of those variables. CP is the total elongation due to pull, right? So that's your correction factor in some number of feet. PM is the pull applied to the tape during measurement. So that would be like if instead of pulling with the standardized pull of say 20 pounds, you were pulling with 30 pounds. So you're really snugging it up. So this would be 30. This would be the standardized pull, which as I said here is 20 pounds. L is the length of the tape. A is the cross-sectional area of the tape. And E is a property called the modulus of elasticity. In other words, it's a representation of the stretchiness of the tape. Now, I've given you values for those because there's not really a reason that you would know those two values. You will, at some point, learn about E if you take mechanics of materials. or any type of a strengths materials course. But for now, we'll just give you a value which tells you that the modulus of elasticity for steel is 29 times 10 to the 6 pounds per square inch. A is the cross-sectional area of the tape, which is also given to you. That's the length times the width of the tape, so it's very, very small. And then PS is the standardized pull. Unless you know differently, you would use 20 pounds. So once again, a correction for pull, tension can either elongate or contract the tape based on the standardized pull. So the rules for doing this is the same. The tape gets longer if the pull is stronger. I'm just writing these down so you'll have notes. These are the notes that I'm posting up to the Moodle page. The tape will be short if the pull is weaker. Okay, so you can do the same thing. Whereas if the tape is elongated, temperature is higher, pull is stronger, then the reading on the ground is equal to the reading on the tape plus the correction. And if it's short, so in other words, if the temp is lower or the pull is weaker, then the reading on the ground is equal to the reading on the tape minus the correction. All right, so the third one that we need to deal with is the sag. And sag, some people get this confused and think about tension and sag. Now, if you support the tape throughout, so in other words, if you lay the tape on the ground, you will still have a correction for temperature, but you will not have a correction for sag. Sag is what is technically called a concatenation or catenary. And the catenary is like, if you look at power lines, the fact that between poles, the power line kind of forms a sagging spot. That depends on a couple of different things, but basically it's the weight of the power line, or in this case, the weight of the tape, pulling it into a sag, and that will always shorten the tape. So sag always shortens the tape. Just writing that down so you have that note as well. So what that means is that the sag correction always works in the same direction. But here's the other part. If you have a tape that's 100 feet long and you pull 300 feet, every time you pull that tape, you're going to get a sag. So this correction, the C sub S, if you had a 100-foot tape and you pulled it 3 times for 300 feet, you can't just multiply this. Well, you have to do it for every time you pull the tape. So in other words, you can't put in 300 here. You would have to do this correction and then multiply it by 3. Or it would be more realistic to say that I pulled it, that my measurement was 284 feet, which means I pulled the tape 100 feet, 100 feet, and then 84 feet. So you could put 100 feet here, multiply it by 2, and then you would have to put 84 feet in the next time and add all 3 of those together for the correction for sag. So once again, that's in feet. Omega is the weight of the tape per unit length, and a value that you can use, a typical value would be 0.4 pounds per foot. The length of the interval between the two supports, once again, if you pull 100 feet, this would be 100. If it was, this number is not correct. I'm looking at this. This should be 0.04. So omega is 0.04 pounds per foot. That means that a 100-foot tape weighs approximately 4 pounds. Otherwise, it would indicate at 0.4, it would indicate that tape would weigh 40 pounds, and you know from picking them up that they don't. So I'm going to correct this on the document that goes on your on the Moodle page. But when you're referencing this, just recognize this number should be 0.04, not 0.4. All right. L is the interval between the two supports, like I said. So if you pull 100 feet or if you pull 84 feet, L goes here. And you notice you have to cube that number, so it's L times L times L in order to make this correction work. And then P is the tension or pull that you actually put on the tape. So if you pull with 30 pounds, P here would be 30 pounds. All right, so those are the 4 correction factors that you need to make every time that you pull a tape. So since sag always shortens a tape, what does that mean? Well, that means that if you have on the ground, if your tape registers 100 feet, that means that the ground is always going to be less than 100 feet. So in order to get the ground, because it's shortened, you will have to take the reading on the tape and subtract the correction. Okay. All right. So this is all of the mathematical information that you need about the correction factors. There are 5 problems for homework here, and they test out all of these different corrections. So I'm just going to go through these really quickly with you. The first problem reads a distance of 78.6 feet was taped. That's the reading. Let's go ahead and write this out. 78.6 feet was taped. That means that that is the distance that is read on the tape. The temperature is 75 degrees Fahrenheit. There's a little mark here that's incorrect. I will correct that to degrees instead of a dash. In a sloping meadow, which puts one end of the tape 2 feet higher than the other. Okay, that means that that H for the slope correction is going to be 2 feet. So the first thing that we have is we have a temperature correction because we are doing this at a higher temperature than standard, because we already standardized at 68 degrees. We also have a slope correction. Okay, it says it was pulled with a tensile force of 24 pounds. That means that we have a pull correction or a tension correction as well. So you're pulling hard. That means harder, because if we standardize at 20 pounds, that means that the pull correction is going to elongate the tape. The temperature is higher than what we standardize at, so that means that that is also going to elongate. And like I said, with slope, you always subtract the correct, get the horizontal distance. So what we're trying to do is to get the actual distance in horizontal feet. So we're going to have a sag correction, slope correction that we subtract, right? Because we're going to go, because the reading on the ground, this horizontal distance is always less than the slope distance. We then have a pull and a temperature, both of which elongate the tape. So that means that we have to take the tape number and add the correction. So we subtract the slope correction, we add the pull or tension correction, and we add the temperature correction for number 1. Okay, continuing on, problem number 2, a distance of 99.4 feet was taped between 2 survey monuments at a temperature of 50. Okay, here the temperature is lower, so that means the temperature will shorten the tape, right? On a relatively flat concrete park, that means that we do not have a slope correction at all. The tape was supported full over its length, no sag correction, pulled with a tensile force of 18 pounds. Okay, so that means that we're not pulling hard enough. That means that the pull correction also shortens the tape. So both of these shorten the tape, which means that we subtract them from the tape reading to get the actual reading. All right, number 3, we have a distance of 435.4 feet. It was taped between 2 survey monuments at 82. So on number 3, the temperature is high. That means that the tape is long, right? Which puts one end 3 feet higher than the other. So that's that slope correction. Once again, we're going to subtract that one. All right. The tape was supported at the ends only. That means that we have a sag correction. Okay, sag always shortens the tape, doesn't it? So if it shortens the tape, that means that we are going to subtract it, okay, from the tape. Okay, so I'm just going through this, making sure I get all my numbers correct. And then we pull a tensile, we have a tensile force of 20 pounds, and the tape is standardized at 20 pounds, so there's no pull correction at all. Right. Number 4, distance of, I'm just going to go through this, I'm not going to write these ones down, 4 and 5, but a distance of 25.1 feet was taped between 2 survey monuments, temperature 68. That's standardization temperature, so there's no temperature correction. Put one end of the tape 1 foot lower than the other, so there is a slope correction. Tape was supported at ends only. That means there's a sag correction. Pulled with a tensile force of 16 pounds, so there's a pull. So there's 3 corrections on number 4. Number 5, at distance of 714.6 feet, tape between 2 survey monuments 70 degrees. Okay, so this is a little bit hotter, so we have a temperature correction. Relatively flat, no slope correction. Tape was supported over its full length, no sag correction, and was pulled with a tensile force of 28 pounds. So it's pulled a little harder. So that means that we have a tension or a pull correction as well. All right, so that's it for this homework. I've put the due dates up on your Moodle page. So if you have questions, let me know and get it turned in on the due date. And this vlog is actually for Thursday, April 5th. Okay, so I'll do on Tuesday, April 10th, we have advising day, so there will be no vlog or lab for that day. I'll do another vlog for Thursday, April 12th, and that one will be total station, and after that we'll spend the rest of the semester talking about public land survey system and some of the ways that writing land descriptions fit into legal documents. All right, have a great day.